All right, how's it going? Can you hear me? Cool. Everyone have a good weekend? Good long week without this class? Right on. Anyone do anything cool or just kind of end of the semester stuff? Lots of homework, yeah. Honestly, same. I have a lot of my own deadlines in the very near future that most of which are not related to this class. Actually, yeah. So it's a crazy time for everyone. Cat's awake. Get down from there. No, no. Someone was digging her claws into the window screen. She's already put a lot of holes in it. She knows she's not supposed to be there. No, don't do it again. General question, what is my favorite disaster movie? Well, that's hard. I mean, I do think that in terms of the science being the least atrocious, Dante's Peak is probably the best one. But in terms of ones that just entertain me, I really love 2012, honestly. I think that it's an absurd, ridiculous, stupid movie. And the people making the movie knew that. I think a lot of disaster movies fall flat by taking themselves too seriously. And that's actually one of my biggest issues with San Andreas is not that San Andreas, San Andreas is also like completely incorrect in every conceivable way. But I guess other than the fact that we have a fault that's called San Andreas. But I think it takes itself too seriously, and that really hurts it. Whereas 2012 is fully aware that it's a ridiculous movie, and even though the characters are taking things seriously, you can tell the people who made the movie aren't. But yeah, I've seen San Andreas more times than I'd like to admit, really. Partly for one of my other classes, though. But anyway, I guess it is now 2:00. Yeah. Who else's sense of time is even more messed up by the fact that it gets dark at 5, but it's still like 90 degrees out? Anyway, so the last time we met was only a week ago, but feels like longer ago. And that is when we had our third test. And so what we're going to do today is like what we've done after all the other tests. We're kind of going to go over the general trends and the questions that more people got wrong than right. And then we're going to get into our next topic, which is about metamorphic rocks. So yeah, so our test last time, actually, the average score is the same as it was for the second test. It was the same as it was for the igneous rocks test. But kind of like I expected, it was, generally there were people who did better on one than on the other. And it wasn't like consistent. Cat just knocked a bunch of stuff down. Generally, there were people who did much better on one than on the other, and it kind of varied. But another thing that's interesting about this is even though the average score on this one is the same as for test 2, the sort of range of scores is much broader. So for test 2, there were a lot of people that really did get in that like 55 to 65 range, that really did make it it was much narrower around that 61% average. And there were a few people that did really well, and there were a few people that did really badly, but most of the class was in the middle. And so this means that actually more people did better this time. There are more scores that are above the average, or at least further above the average than before. But at the same time, there are also more scores that are lower, like more below the average. So if you noticed yourself being one of the people that did pretty close to average the last time and less than average this time, definitely like think about how you're studying. Think about what you're doing to prepare for this class. If you want to talk with me about how to improve your studying habits and preparation before the next regular test and before the final, I'm really, really glad to help with that. In general, people who come to office hours do better and better over the course of the semester. I've noticed that with literally every class I've taught. So if you're kind of and one of the people that got further away from average on the negative side, like I would love to help you. Just let me know how I can help, or just even say, I don't know what to do. How can you help? But if you're one of the people who are further above the average than you were last time, that's awesome. Keep doing what you're doing. It's also, of course, always okay to ask me for help and talk about things. But yeah, in general, the fact that there are larger numbers of people with scores above the average is a really good thing. But a thing I will also mention is the average time that people took to do the test went down this time. So for test one, y'all took like 40 minutes, and for test two, y'all took like 37, and now you're down to 35. And so I'm hoping that's reflecting the fact that you're all feeling more confident. But at the same time, like use the 45 minutes if you have it. Like use everything you have. Even if you're like, if you feel super awesome and are sure you didn't miss anything, just make sure if you have any time left, just go back and read everything again. Make sure that you didn't misread the order of something in a question. Make sure that you didn't miss something, and do the extra credit if you have time left. I mean, the worst thing can happen is that it's a wrong answer and it doesn't count for anything. It doesn't negatively affect your grade if you don't get the extra credit right. The best that all it can do is improve your grade. So just definitely like use those 10 minutes, like use all the time. As in the past, like the people that have gotten the best scores have either been the people that finished like really fast because they just had it, or the people that took the whole time and were really careful. So any questions about this before I go on to the specific questions? Then I'm going to go on to the specific questions that more people missed than didn't. And it's about the same number of them this time, which is good. So and they were about different things. So and it's not like everybody's missing the same questions, which is a good sign. But yeah, so the first one that a lot of people missed was this one. So it was, in which depositional setting are you most likely to find conglomerate? And so if you remember, conglomerate is it's a clastic sedimentary rock with a lot of different sized clasts that are rounded. And so the critical thing about this was remembering that it's rounded and what allows things to become rounded. If you remember, we talked about like tumbling rocks and how the longer something travels, the more rounded it's going to get, because all those sharp edges that might form when it first just breaks off of another rock are going to get bashed against things as it travels down a river and eventually get smoothed out. And so you're not going to get that at the top of a mountain stream, because the top is where everything is freshly broken. And so you're more likely to get a breccia, which is a similar structure, but everything is really chunky and angular. You're not going to get it in a lake because a lake isn't moving fast enough to have a mixture of clast size. You're only going to get really little tiny clasts falling very gently in a lake. So it's that downstream in a big river, because it's been traveling a long way in a lot of water, and it's been really smoothed out. So that is why B is the answer. So any questions about that? Cool. So the next one was a related concept, and it's again remembering that idea that the amount of smoothness of the clasts, the roundedness of a clast, affects how long it has been transported is the key difference here. And so if you find a sedimentary rock with very angular clasts, that means it just hasn't been transported very far. There's plenty of things that make angular clasts that aren't gravity. Like, yes, gravity definitely makes angular clasts, but it's not the only thing that does. You can have root wedging, you can have exfoliation from fire, you can have a geologist hitting something with a rock. Also, with generally it is mechanical weathering that does this, like, because it makes cracks. But if a chemical weathering process is removing just the soft stuff between the crystals, like if let's say you have a chemical weathering process that weathers away the feldspar but not the quartz in a piece of granite. The quartz crystals are pointy, they're chunky, they're not rounded. And so you can still have chemical weathering free up very pointy things. So generally, when roundedness versus angularity is very much a measure of transportation. And so C is correct. And so definitely, this just A and C was the best wrong answer, because most of the time you get chunky stuff from mechanical weathering, but it's not the only thing. So does this one make sense?
Yes.
Wait, did someone say something, or it was very quiet if you did?
I think they just said yes.
Oh, okay, cool. All right, let's move on. So this one, which of these steps has the largest control of the final composition and structure of a sedimentary rock? And most of y'all said lithification. But the fact is that lithification is just working with what's already there. Lithification is that process of cementation and compaction. It's that process of packing whatever is there into a rock. But what is there depends on what got deposited there. So lithification is going to work the same in pretty much everywhere. But what is getting lithified depends on what got deposited there. So that's why when we talk about, these sedimentary rocks form in rivers versus lakes versus the ocean versus kinds of things, those aren't lithification environments, they're deposition environments. They talk about what got dropped off and how. So it's good that this was the second most chosen answer. But the correct answer here is actually deposition. Once it's lithified, it's just locking everything in place. So does that make sense?
Yes. Now that you explained it, it makes a lot more sense.
Does anyone have any more questions about that? All right. Okay, so then this next one, which type of mass movement is the least likely to give you an advance warning? The answer to that is a debris flow. So debris flows they start when they're going to start. You never really know exactly when there's going to be enough water to get a bunch of stuff loose and start flowing. Slumps are very, very slow, and they form cracks in the land before they start moving, and people can see them in advance. Generally, landslides, even though they're faster than slumps, are still, they give a lot of warning before they move. Once they start moving, if you're not out of the way, you're kind of screwed, but they're going to give you a lot of warning that it's about to happen. If you remember that video from Japan where that entire hillside just went and went and went, and everyone was standing there going like, what? But that was, they knew to mark that off and to be there waiting because they saw signs of the hillside starting to crack and fail. So there was a lot of warning, even though it then moved very quickly. And a sinkhole, that's another thing that sometimes moves pretty quickly, but you can generally get a sense that that's going to happen because it's the ground surface falling into a hole. And so it's not going to go from zero to just in a second. You're going to start to see the ground kind of cave in and sink and dip. Like you're going to see an indentation before the whole thing caves in. And so similar to like a landslide or a slump, you're going to see a bunch of cracks around the area that's about to fail. and then it'll eventually fail if you're looking for them. Like I know someone's going to go, well, did you see that on the sinkhole in the street that I lived on? And in hindsight, yeah, there are a lot of cracks in that street, but it wasn't really anything anyone was thinking about until it happened. But a debris flow, like you can identify sort of the places that are more likely to have one. But once it started, and they're really fast, and there's kind of nothing you can tell until it's there. So that one good? Any questions about this one? Cool. All right, so this next one about divides. So the correct answer here is that, so the question is, you're standing on with one foot on either side of divide, and you pour a glass of water out of each hand. What happens to that water? And the correct answer is that the water from one hand drains to one ocean and the water from the other drains to another. A divide is really completely splitting everything. If something pours down different sides of the divide, it's never going to meet back up again. So this second, the answer that most people chose is that the water goes into different watersheds, which is true. But it's just not going to come back together at all. Like this is the kind of thing, I mean, eventually I guess it could circulate around the entire planet, but like the Gulf of Mexico water and the Pacific Ocean water are not going to run into each other very easily. They really just pour out into completely different directions. They don't dump into the same ocean or into the same river. It's just really the like completely different directions. So does that make sense now?
Actually, can you explain that one more time for me?
Yeah, so a divide just means it just means everything is going in opposite directions to opposite places. So in this case, like, so B would imply, yeah, they go into different small streams, but still meet up again before reaching the ocean. And B implies that it's going kind of in different directions, but empties into the same place. But really a divide means not only is it going to a different place, it's emptying into a different place. Like it really is, everything is going somewhere different. So like the Great Divide in the Rockies, like on one hand, like your water's going to go, if you drop stuff on the west, it's going to go to the Pacific. And if you drop stuff on the east, it's going to go to the Gulf of Mexico. Like the end destination of that water is not the same if stuff is coming from either side of a divide. Does that make sense? Does that answer your question?
Yes, it does. Sorry, I thought you saw my thumbs up.
Oh no, I don't necessarily see everyone all the time because there are 33 of you, and I have to click through everything. I also don't actually see your video today. I see you have a black square.
Would you like me to turn on my video? I can turn on my video.
I mean, you don't have to. Oh, your thumbs up over there. Oh, you don't have to turn on your video. Okay. Sorry. Okay. But yeah, I guess your thumbs up didn't show in the participants list. But anyway, cool. Any other questions about this? All right. So there was one more that more people got wrong than right, and that was this one. So, but just barely. So it was, what do moraines indicate? And they indicate all of those things. They're the edge of a glacier, the former, like where the sides of the glacier were, where the tip of the glacier was, and where sort of the boundary between two glaciers. Like if you have two glaciers coming down very close together, there might be sort of an edge of rocks where they meet. So definitely E was the best wrong answer, but it was still a wrong answer. A moraine can actually be every single one of these things. And if you and there's a diagram of that in the slides if you want to look at that again. Definitely the ones that mark the edges are the most common, but it can be all of those things. So are we good on that? Okay, so those were all the ones that most people didn't pick the right answer. So, and again, if you want to go over your own test specifically, like any of the other questions, you can come to my office hours. So I have them tomorrow from 2 to 4. They're Tuesdays from 2 to 4, although I probably won't have some next week because it's the Tuesday before Thanksgiving, and I don't think anyone's going to want to do that. But I'll let you all know. What I will probably do actually is cancel those office hours next week, but then have an extra review session before the final. But we'll talk about that later. So you can always email me questions. If you can't come to my office hours, I'm happy to make an appointment to go through your test on Zoom. I want to help you all learn, but you have to ask me the questions that you're curious about. But anyway, that was this for this test. We have one more of these, which is on December 7th. It's the last day of the regular semester. And it'll be like this one. It'll be the 30 multiple choice questions. We will have the review session before. There will be 3 points of extra credit, which amounts to 5% of the grade. And then our final is the following Monday. It is December 14th. It is from 3 to 5. And it will be an open note, open book, open canvas, open everything except talking to other people or asking things on message boards. So you'll be able to use all of the notes and things for this class. But it'll also be a lot more interpretive. So it won't necessarily be like something where you can look up the answer so much as you can look up the information that you need to determine the answer. And that won't be multiple choice. It'll be 6 questions that are like written questions. So just keep that in mind. And it won't be on Lockdown Browser. But I'll have an extra review session before that. But in terms of sort of looking at, we're now most of the way through the semester. And so there's like a little less than maybe about a quarter of the stuff left. So, and the first extra credit was due today. So if you didn't already do the Dante's Peak extra credit, you did miss the Dante's Peak extra credit. And now that that's done, I'll try to grade those either tonight or tomorrow. And get those up to date. But in terms of all of the grades that are up, everything is up to date except for the vocab and quiz that were due today and the extra credit. Everything else is graded so far. So if you're kind of still not thrilled with how that's going, or even if you are and you just want an extra safety buffer, just in case you happen to end up super confused by Metamorphic Rocks, there's going to be another extra credit, and I'm going to introduce that today. It's going to go up after class today, along with the first Metamorphic Rocks quick quiz. And so the next thing we're going to do is we're going to watch another excellent geology themed movie. And you're going to do another set of questions. And so the movie I'm talking about this time, do not curve the tests. No. The tests are worth 30% of your grade. The regular assignments, including the extra credit, is worth 50% of your grade. So by doing the extra credit, it helps, you can push your regular assignments grade, that 50%, to more than 50%. But yeah, and then the final is its own 20%, but it's interpretive. It's a lot more flexible. But yeah, when in doubt, and especially if you're worried about things like how those different parts of your grade are stacking up, I would recommend doing this next extra credit. And so we're going to watch a very fine recent geology movie, by which I mean this. We're going to watch Moana, and you're going to do some extra credit questions about this. And I'm not just saying that this is a geology movie because it stars The Rock. There's actually a lot of really good attention to geologic detail in this movie. There really are, like, when I saw this, I mean, first of all, the bad guy's a volcano demon, which is awesome. But also, like, just the detail in the landscapes of this. Like, I can tell you exactly what this rock is that they're standing on. It's basalt and it's pahoehoe, because you can see these flow marks from the lava cooling. There's a lot of really awesome geologic detail in this movie in a lot of different ways. And so I'm going to want you to watch this. So the questions for this will go up after class today, and just sort of if you haven't seen this before, it's great. If you have seen this before, you're going to be watching it from a geologist standpoint, and you're probably going to notice a bunch of stuff that you never noticed before. So that's going to go up after class today, and it's going to be due on the very last day of finals week. So it is going to be due at 11:59 p.m. on December 15th, which is the day after our final, but that is the last day of finals week. So it is due as late as you can possibly do something. So any questions about that? Or about any other test grade, anything things? You did not expect this at all. No one expects this. That's why it's fun. Yeah. Cool. Are we good with general questions or concerns? Should I move on to our new topic? Gonna move on to our new topic. If it lets me. Hello. Where is it? Would be cool if it would let me share the other presentation. Come on. Why do you, okay, there we go. I had to quit PowerPoint and restart PowerPoint. Okay, do you now see a definition of a rock and not the rock? Okay, cool. Of course, that made the chat window disappear. Okay, so as we've been organizing the class so far, so first we did the groundwork on how the Earth is structured. Then we had our igneous rocks and volcanoes, our sedimentary rocks, and the surface processes that cause them. And now for the last part, we're going to talk about metamorphic rocks and the processes that cause those. And so if you remember, our definition of just a rock is it's a coherent, naturally occurring solid. It consists of an aggregate of minerals or sometimes a body of glass. And so hopefully by now, this is a very familiar definition. And so we have our three groups. Our igneous rocks formed by solidification of molten rock, either under the ground or above it. So either erupting out of a volcano or cooling sort of inside the earth, but not too deep. Then sedimentary rocks formed by fragments of stuff that have been cemented together or precipitated from solutions, and that inherently happens on the surface. Those are all about surface processes. So igneous can be surface or below the surface. Sedimentary is all surface process all the time. But metamorphic rocks, they're formed when pre-existing rocks change structure and or composition due to changes in the pressure, temperature, or surrounding chemistry. And so metamorphic rocks are almost always something that happens inside the Earth. They're almost always, with the exception, there's a few rare cases that it can happen on the surface, like when you get hit by a meteor. Yes, we're going to talk about that next class. But for the most part, metamorphism occurs inside the Earth and is very, very related to plate tectonics. So igneous rock stuff is super tied to plate tectonics. Sedimentary rock is not very tied to plate tectonics at all. And metamorphic rocks, for the most part, most metamorphism is very related to plate tectonics. So that's going to come back a lot in this. And so today we're going to introduce some concepts of just what metamorphic rocks are and what causes metamorphism. And then next class, I am going to show you some rocks today, but next class we're going to go through the different specific settings of metamorphic rocks, where they form, what kind of rocks you can expect to find in each of those settings. And we're going to go over some charts that help you sort of tell how metamorphosed a rock is based on its structure, based on what minerals are in it. There'll be charts next class. There will be homework based on the charts after next class, but there are also charts that you will get to use on the test. But I'm getting ahead of myself. Let's just introduce metamorphism first. Although, are there any general questions before I do that? Cool. All right. So a metamorphic rock, again, it forms when a pre-existing rock undergoes a solid state change in response to modification of its environment. And so let's pick that apart. So pre-existing rock, you can't just go from zero to metamorphic rock in nothing. Like there has to be, you have to start with either an igneous rock or a sedimentary rock. And whatever it is, that rock is called the protolith. So lith, again, is rock, like lithosphere, like lithification. And proto is like, it's like a prototype, you know, or a protoplasm or a proto, you know, it's the sort of predecessor to the not quite finished version. It's kind of the beta of this rock, I guess, except it is a finished rock. It's just not a metamorphic rock yet. The protolith is what turns into something else. And the protolith can be anything. It can even be another metamorphic rock. But the whole thing is that by definition, a metamorphic rock starts as something and becomes something else. But it has to do that in a solid state. So that means if it doesn't melt, if it melts, the second there's melting involved, it's an igneous rock. Like the second, I mean, you can have like little tiny bits of it melt, but the second the entire thing melts, it's igneous. So it has to change state while solid. It cannot become a liquid. And that's in response to modification of the environment, meaning in this case, the environment inside the Earth. So this doesn't mean like, oh, it's going to rain and you're getting metamorphic rocks. No, this means a modification of things like temperature or pressure or movement inside the Earth, how much something is being squished or pulled or heated. Or sometimes it means an introduction of other chemicals to the mix. But all of these things turn one rock from another while keeping it solid. And so that always changes the structure of the rock. It always changes the crystal structure or the way the rock is stuck together. But often it also involves turning minerals into totally different minerals. So you can have a thing where you're going to have the exact same minerals that are just organized differently. That's a structural change. But you can have things where the before and after look completely different because the metamorphism is so extreme that every mineral has turned into something else and arranged itself in a totally different way. So what we're going to do today is talk about how those things happen. But are there any questions about this this definition, any of this? Cool. So some metamorphic rocks look very similar to their protoliths. So this is example, so this is sandstone on the left. It's just a good old chunk of white sandstone, your classic clastic sedimentary rock. And on the right, you have quartzite, which is basically a metamorphic sandstone. So as the name might suggest, it's mostly quartz, but so is sandstone for the most part, especially this white sandstone. And these look really similar. Like you can still see they're kind of grainy. This is not necessarily something that you would definitely go, oh, these are super different looking rocks, even though these formed in super different looking conditions. Basically, if you were to pick this apart or look at it under a microscope, or even like honestly with a sandstone, you can like kind of scratch it apart pretty easily just because of the way it's stuck together. With quartzite, it's a lot more solid. It's a lot more dense. In general, metamorphic rocks are a lot more dense than other things, but because they've been compressed. But yeah, sandstone and quartzite, they have the same stuff in them. But the sedimentary rock here is just lithified grains. Remember, it's grains of sand that have been cemented together by mineral-rich fluid and then compacted until it's stuck together. But the metamorphic one, in this case, has experienced enough pressure and temperature change compared to that sandstone that the quartz in it rearranged itself, not into grains that weathered out of something else, but into crystals, into newly formed crystals that are actually stuck together through atomic bonds rather than through cement. So that's still a structural change, even though these are very similar looking rocks. So does this make sense? Quartzite is very common, by the way. I mean, sandstone is a very common rock, and quartzite is a very common rock. So sometimes you get this, and you might go, well, that's kind of boring. It turned from a white rock into a different white rock. But sometimes you can get really wacky stuff like this. Sometimes the metamorphic rock is going to look nothing like what it used to be. So in this case, the protolith is shale, and it's red shale in this case, which means the red indicates there's a lot of iron in it. And so shale, if you remember, is this very fine-grained sedimentary rock. You can see these ripple marks in it, which means that it formed probably in a river or maybe a lake. But yeah, shale is very sedimentary, and this is red. But after a lot of temperature and pressure changes, it turns into this thing on the right. Well, and this is called gneiss. So it's spelled Gneiss. It's pronounced nice. And this is made of the same atoms. It's just that the temperature and pressure changes were enough to basically break apart all the chemical bonds in the shale, and all of those atoms stuck themselves back together into completely different minerals. And so in this case, because there's a lot of iron in here, you have a lot of dark colored mafic minerals because of that iron. And you have the lighter color stuff forms bands. So in this case, yeah, the shale, like if you were to look at this, would you, if I hadn't told you these rocks were related, would you have ever guessed these rocks were related? Yeah, not at all. But that's because the temperature and pressure changes inside the Earth, and especially in places where you have convergent boundaries, where plates are crashing into each other. The forces, the pressure and temperature is so extreme that it can do stuff like this. So yeah, that shale has lithified grains of sediment, again, like the sandstone. They're in random orientations. There's grains and cement, and whereas the gneiss has totally different minerals. And because of the pressure situation, those minerals align themselves into these bands. So this is both a chemical change and a structural change. And we'll be talking about both of these both of these types of change today and next class. Any question? And I'll talk more about, this says foliation. I'll talk more about that, and I think it's the next slide, maybe the slide after that. But any questions about that so far? Okay, yeah, it is this slide. So there are two main structural classes of metamorphic rocks. So your foliated rock, like your gneiss here, this is another piece of gneiss. It's that the mineral crystals either form or reorganize into these parallel interlocked layers based on their composition. So this is not like sedimentary rock layers or like layers of lava flow where stuff is just piling up and piling up and piling up. This has nothing to do with that. This is just that the entire rock was heated and pressurized in a way that the chemical bonds broke and found each other, and sort of things bond with like things. This all has to do with atomic bonds breaking and reforming in these layers based on sort of just the composition, based on what stuff it finds. And usually, if you were to look at one of those, we'll talk more about this next time, but usually this is what we call a metamorphic fabric. Because if you look at it, like if you were to look at a sheet of actual cloth, like if you look at a piece of woven cloth, you're going to see that the threads are all aligned in a direction. And in this case, the rock fabric, all of the grains of minerals, all of those crystals are going to be aligned in a direction that's related to the way the pressure was coming from. So generally, if you squeeze something from above to below, you're going to get horizontal things. And if you squeeze it from side to side, it's going to make vertical. So all of this banding is just related to atoms finding atoms that it wanted to bond with when the temperature and pressure break all the bonds. So foliated rocks are going to be stripy or are going to have a visible textured fabric. Meanwhile, non-foliated rocks like a quartzite are just the grains, and they're in alignments that aren't related to chemistry. They're still going to generally align themselves in a way that's related to pressure, but they're not going to break apart and find other minerals and change their, they're not going to get foliated layers like that. You're not going to get that kind of reorganization. The organization is just about pressure, not chemistry, whereas in foliated, it's about both the pressure and the chemistry. So does that make sense? And it's generally going to be pretty easy to tell just from looking at something, whether it's foliated or not, because you're going to see the stripes, you're going to see the banding. where you're going to see a sort of layered, like something that looks like the texture of a piece of fabric. And so what I'm going to do next is just show you some examples of them. There's going to be a lot of rock names all at once. Don't worry about them too much yet. Part of the reason I'm going to do this next is just because these are names that are going to be on charts. And we're going to go into the more detail about these rocks that I'm going to show you next on Wednesday when we talk about where they form. I just want you to like have heard these names before, so you're not looking at a chart and going, what the heck is that? So yeah, there's a lot of different kinds of foliated metamorphic rocks. And so like you can get slate, which is basically just kind of like shale, but squished even more. Basically, each of those go from the least temperature and pressure to the most temperature and pressure for the most part. Like slate, and like you can see here, there's layers in the slate. So even though you can't necessarily see colored stripes, it's something you can break apart very easily on those layers because you have stronger versus weaker rocks, or weaker minerals, excuse me. You can have phyllite, which comes from also layers, from a Greek word for layers. And here you can see, again, there's, even though they're all the same color, can you see how these are kind of rougher, and then you have a smoother band, and then a rougher band and a smoother band? Do you all see that? You can have schist, which this is a garnet mica schist. So these are garnets and these are mica. This is one of the shiniest rocks you will ever find. And this is another one where if you look at it, you could see like it'll be sparkly in one direction, but less sparkly in another direction because of the foliation. And if we were in a classroom right now, I would pass a piece of this around, but we're not. You can get metaconglomerate. So this is what happens when you take a conglomerate, a sedimentary rock, and do this. So some of this is pre-existing clasts, but some of this is they're organizing into bands between them. So very often, like you can say meta something, if you can tell like what it used to be sometimes. Then you have gneiss, where you can, gneiss, the stripes are super easy to see, nice stripes. And then migmatite is just barely still a metamorphic rock. So in this case, you can see bands like a piece of gneiss. But this area here is where it did start to melt, but it didn't melt the whole thing. So it was a pocket of melt inside an otherwise metamorphic rock. So it doesn't quite count as igneous. It's still metamorphic, but just barely. So these are names that you're going to see on charts we're going to talk about. I will reintroduce all of these next time. So again, don't stress about it. But these are, can you see though that there's either layers of color or texture or different things in all of these? Yeah, so schist can be a lot of different colors. Yeah, I do think that looks kind of like an ocean. Next time I'll go get my really cool piece of schist with garnets in it that I got from the Alps. I'll bring it to class and point it at the camera next time, I guess. But yes, in case you're wondering, specifically about gneiss and schist, you're like, yes, it's everywhere. Yes, the joke has been made many times. Why are you so nice? Because I'm not full of schist. Take me for granted. You know, this was like the first page of the Google search. You can find infinite gneiss and schist puns, infinite. Geologists are insufferable. But yeah. In terms of non-foliated though, well, actually, before I do that, any questions about these? Cool. Okay, so non-foliated metamorphic rocks don't have that layering. And I know you're looking at that marble and going, that super has layers. So the difference with marble, I'll talk about marble in a second. So quartzite is just chunky grains. They're not aligned. Hornfels is kind of like the kitchen sink of metamorphic rocks. Like if it's kind of not anything else more distinct, it's probably hornfels. And it's worth noting though that this fels is from the German word for boulder, not Forum Felsig. So this has nothing to do with Mafic or Felsig. It's from German. So I'm not going to ask you about that, but just don't let this name confuse you. This one can be mafic. This one looks pretty mafic. They can be kind of felsic. They can be whatever. It's basically, if it's not anything else, it's probably hornfels. Quartzite is metamorpho sandstone. You can see these don't, this is a white rock. This is a black rock. It's chunky. It's not particularly distinctive looking. Meanwhile, marble. So the reason that this doesn't count as foliated is, so marble is metamorphic limestone. So most of what we've been talking about is silicate rocks, or things that came from your quartz and your feldspar and your amphibole and all those minerals we talked about way at the beginning of the class. But marble is a carbonate. It comes from limestone and calcium-rich stuff. And in this case, the layers in marble are not from they're not from bonds breaking and restructuring. They're just that this stuff was already in there because it comes from a sedimentary rock that has layers. So this stuff was already in there. It just kind of gets smushed and smeared and structurally changed without actually organizing based on layers. So you can have marble that has no layers in it at all. And you can have marble that has layers in it, but that just means that the protolith also had layers in it. Marble is not as intensely metamorphosed as things that completely change their mineral content. So does that make sense? Yeah, all of these form inside the earth. Usually, I mean, inside the crust. Like, by the time you get into the mantle, it's too hot for this to happen. So this is inside the crust. And we'll talk a lot more about where all of these different ones form on Wednesday. But yeah, any general questions about these? I promise we will come back to all of them next class.
I have a question.
Yeah.
So for marble, given enough time, will the layers, like the foliation on the rock itself, become like more intense?
So this, I mean, this isn't foliation. So if it were to change its structure and break all the bonds and have the minerals reorganize themselves differently, then it wouldn't be marble anymore. It would be something else.
Got it. What would that rock be?
I'm blanking on the name of what that rock would be. I can look that up, but it's not marble. Basically, the chemical composition is useful for metamorphic rocks, but a lot, like when we classify them, it's a lot more about like what temperature and pressure did it form in, because what it'll turn into depends on what temperature and pressure it's in. So like under certain temperature and pressure conditions, limestone will turn into marble, but under different temperature and pressure conditions, it'll turn into something else.
Okay, yeah. Got it.
And often you can tell what the conditions must have been by looking at the rock. So anything else before I go on to like how these changes happen? So as I was just saying, there's a lot of different kinds of metamorphism. There's a lot of different things that can cause a rock to fundamentally change its structure and or chemistry. But the main suspects are heat and pressure. That's where it's all at. So you can have metamorphism that only occurs from heating. And you can have metamorphism that only forms from pressure. Most of the time, both high heat and high pressure are involved, or some combination of heat and pressure. Then you can have situations where you have high pressure and shear. So, excuse me. So shear is the process of rapidly sliding things past each other. So pressure is just squeezing and squishing, but shearing is actually frictional sliding. So you know how we talked about frictional sliding with landslides, we talked about frictional sliding with glaciers. When we talk about earthquakes, that's all frictional sliding all the time. But that process, when you think about lots of rock sliding past each other, generates a lot of force and a lot of directional force, a lot of directional change, and also some heat that is very oriented with the direction of movement. So shearing rocks, grinding them past each other, slowly or quickly, especially quickly, can also cause metamorphism. And then you can also have a thing where our good buddy, the hydrothermal fluid, is back, our warm liquid with a lot of minerals in it, our molten minerals in water situation. So that can, those traveling through rocks can provide by itself, it's not necessarily going to do metamorphism. There's usually, well, I mean, it will do it by itself if it's really, really hot, but it has to be like really, really hot. But usually it's some combination of a pressurized situation with a mineral-rich hot liquid that can really, really mess with the chemical structure of things. So kind of these are the cases that you're going to get metamorphism. And next class, we're going to talk about different environments, and I'm going to sort of classify this by like, this is heat, this is pressure, this is both. But there's also, given these different conditions, there are different kinds of changes that happen. So you have conditions that lead to change, kinds of change that can happen, and then places where all that happens. So today we're going to talk about the kinds of change under these conditions, and next time we're going to talk about the places and the specifics. But any questions about any of these before I go on? Cool. So if those are our 5 general conditions, there are actually another 5 processes. So when it says on your study note-taking guide, the metamorphic processes, these are what I'm talking about. And you've probably heard, well, if any of you, well, you've all heard of the last one before, right? So we talked about plastic deformation when we talked about glaciers, because that's how the individual grains of glacial ice move around and change during the formation and motion of a glacier. But do any of these other things sound like something you've heard before? Yeah, so phase change. So can you say what that is in the context that you've heard it before? No, okay. Has anyone else heard of phase change before? So you might have heard it in the context of like, think back to your, basic chemistry classes, your basic physical science classes. Yeah, it's going to hopefully sound familiar in a second. So basically a phase change is like when you're changing from a state of matter to a different state of matter, right? Like when you're changing from a phase change is when water freezes and becomes ice, or when water evaporates and becomes, when water evaporates and becomes gas. Yeah, a phase change is where you have the same stuff changing form. No, you're not dumb. It's not dumb. It's just like, it's something you don't think about that much. But yeah, it's a thing that's like, everyone knows that water freezes into ice and evaporates into vapor, but thinking of it as a phase change is like, oh yeah, no, don't feel bad. Like if you totally knew that, but didn't realize you knew that. Like that's why we're talking about it. But yeah, in the context of, it's basically the same thing in the context of rocks too. I mean, they're not melting and evaporating, because if they were melting, it would be an igneous process. But a phase change in this case is stuff that is made of the same atoms, the same minerals, one of the same chemical building blocks. It has the same chemical formula, but a very different form. Like ice, water, and water vapor are all H2O, but they have a very, very different structure. The atoms are fit together in very different ways. And that is exactly the same thing with minerals. So as it turns out, minerals have phases. So when we talked about minerals, every mineral has a chemical formula. So like the chemical formula for quartz is SiO2. Quartz is always SiO2. But SiO2 is not always quartz. Just like water is H2O, but H2O is not always liquid water. H2O can be ice. H2O can be water vapor. SiO2 can be quartz, and all quartz is SiO2. But based on the temperature and the pressure, that organization of those silicate tetrahedra, they're back, I'm sorry. I'm not gonna actually make you do structural stuff with them this time though, but they're back. If you remember with quartz, those tetrahedra, which are diagrammed here, the silicate in the middle and the oxygens on the sides, have that very loose, spiky framework silicate structure. And so this is not a very dense mineral at all, and it forms under low pressure. forms in the upper crust on the continent. But if you pressurize that quartz, if you pressurize it, under moderate pressure, those tetrahedra reorganize into something that's more dense. So they're still tetrahedra. They just sort of fill in more of the spaces. It's still kind of a framework, but a much more tightly packed framework. And so that forms a mineral called coesite. And coesite is still SiO2, but it is not quartz because its structure is different. Its crystal habit is different. It has a different, like if you remember way back from the beginning when we did all of those things like fracture and cleavage and streak. I guess the streak is probably the same because it's all silica. But all of those tests, like the hardness is going to be different because the whole thing fits together in a different way. And then under super high pressure, it changes again into something called stishovite, which is actually a very rare mineral. It's very, very rare to have a situation where silica is solid at pressures and temperatures enough, at temperatures that allow this to form. So stishovite is extremely rare. But that's another case where the tetrahedra align themselves in even weirder, in a much more, not quite sheety way, but like almost. And so this is the kind of thing where this is the most dense, the most air, and then this is more compact, and this is more compact still, which makes sense. If you squish something really hard, it's going to compact. So if you can think of it that way, that it can hopefully help you remember this. But basically, this is a way that like you can have the exact same chemical composition, but ultimately different minerals just because of the structural change. Because when you crush something, it's not the same shape it was before. In this case, you're not shattering when you're crushing it under metamorphic conditions. So does this make sense? So these phases are all solid. So it's not like solid, liquid, gas, but it's that same idea of changing structure. Any questions about phase change? Cool. So the next two I'm going to introduce at the same time because they are related. Well, I mean, they are similar enough names to be potentially confusing. So I'm going to talk about recrystallization versus neocrystallization. And so your book is also going to use a different word. Your book is also going to say metamorphic reaction. For neocrystallization, I'm just going to say neocrystallization. I like it better. But also, I think that these names, even though they sound super similar, if you just remember what that prefix means, it's going to tell you a lot about the difference. So like in recrystallization means over and over, like repeat, rewind, you're doing it again, you're going back over, you're recreating something, you're making it again. So to redo, so recrystallization is the same thing over and over and over. It's basically that you're turning mineral grains into larger crystals of the same mineral. So that idea of like, this is what happens between sandstone and quartzite, is that in sandstone, you have tiny little grains of sand that have weathered off of larger quartz-rich things that have gotten cemented together and lithified. But then under metamorphic conditions, it basically causes all of these little grains to glom together into larger crystals. And so that's why if you were to look at that sandstone under a microscope, you'd see little bitty sand grains. And if you were to look at a quartzite, you would probably see larger, more solid crystals. Because this is all still quartz. It's all the same stuff. It's just the chemical bonds have become kind of loose enough that the crystals kind of come together. So recrystallization pretty much always makes the grains get bigger just because it's a bunch of stuff of the same type getting stuck together. So does that make sense? Meanwhile, neo means new. So in that case, neocrystallization is you're making new crystals. You're making different crystals. So in this case, like you can start with something that's made out of a lot of clay and quartz, like again, that slate. Yes, shale from the first slide. And so it's just a mix of, gray rock, gray sediment. But neocrystallization, basically all of the bonds break so much that things form together into totally different minerals. So in this case, you start with clay and quartz, but when you break apart the chemical bonds under those right pressure and temperature conditions, it forms back together into quartz and garnet and mica. So it's all of the exact same atoms as before. They're just organizing into different minerals. And so garnet in particular, if you find garnet, it's an indication of pretty high pressure, because garnet is something that can only form under a certain amount of pressure. Yeah, so recrystallization, making bigger, newer crystals of the same stuff. Neocrystallization, you're going from crystals of one kind of mineral into crystals of other kinds of minerals. All related to temperature and pressure. So do those make sense? Do you understand this difference?
I'm having a little trouble with neocrystallization.
Okay.
So it's taking old crystals and turning them into new crystals?
It's taking, I mean, yes, basically, it's taking crystals of one group of minerals, breaking apart all the chemical bonds, and then crystals of different minerals form. So
Okay.
yeah, you could say this is old and this is new. Yeah, because this is the rock, this is the protolith, and this is the newly formed metamorphic rock.
Okay. I think I understand it a little bit better. It's just interesting.
I mean,
Yeah.
it's pretty intense, and we'll talk more about how this happens soon. But it's just, you know, under certain conditions, atoms are going to attach to each other in different ways.
Mm-hmm. Okay.
And
Thank you.
so, sorry, yeah.
Oh, I said thank you.
Oh, okay. Cool. Anyone else have questions about this? All right. So the next one, this is one we haven't talked about before, and this is called pressure solution, which if you think about the name, hopefully it'll help you remember what it is later. It's pressure, it's under a lot of pressure, and solution, there's stuff dissolving, there's liquids involved. And so basically this requires water, or it requires a hydrothermal fluid. It requires hot water with minerals in it. And so under pressure, this is going to do a couple of things. First of all, just pressurized stuff is basically going to be forcing other atoms or forcing water into the chemical structure of the existing grains. And that's going to help break them apart. So that forcing is going to help dissolve the edges of the grains or crystals in the protolith, and just start breaking apart the edges, kind of like a form of chemical weathering. But then because it's under very high pressure, it's also going to work its way into the chemical structure of what's there. But then because you've got a fluid, you've got a liquid, it's going to flow from something that's less, the area that has more pressure to the area that has less pressure. And so the area that has more pressure is where there's more solid stuff. Obviously, if you're trying to fit a bunch of stuff into a very tightly packed space, it's going to be, excuse me, it's going to be more high pressure. Whereas the spaces in between are going to be lower pressure. And so all of that mineral-rich liquid that is kind of exchanging its own minerals with the existing grains and is also taking stuff is going to flow into any gaps between grains. And this especially happens in clastic sedimentary protoliths because the cement will weather away and get torn up before the clasts will. But then that fluid will flow into the gaps, will flow into the low pressure places and deposit minerals, will deposit more atoms. And then depending on the pressure and temperature situation, what forms might be something that only forms under metamorphic conditions. It just depends not only on what atoms are there, but what pressure and temperature allows them to stick together in what ways. So does that make sense? I think this is one of the most confusing ones, but does this make sense? Any questions about pressure solution? Okay, and if, you know, we'll talk about this more just a little bit next time, but this is something that like, feel free to ask again if it's confusing later. Then I'll move on to the last one. So this you've seen before. You've seen this exact image before because I put it in the glaciers lecture, even though it was from the Metamorphic Rocks chapter. So a lot of things are extra applicable. But plastic deformation, again, does not involve literal plastic. There's no literal plastic inside the Earth. It has to do with solid material behaving like it's plastic. So like how the mantle convects, how the lithosphere, or not the lithosphere, the asthenosphere flows, even though it's still solid rock. It's that idea of temperature is really, really hot, so things are soft, but pressure is high enough that it prevents things from melting. And so you have a bunch of very soft, very hot rock that smears and flows, but doesn't melt because the pressure is too high for that to happen. The pressure is too high for the atoms to spread out and become a liquid. So in this situation, again, it requires both very high temperature and very high pressure, especially high pressure. But in this case, it changes the shape of the grains without breaking them. If it broke them, it wouldn't be plastic. It would be brittle. So the opposite of plastic is brittle. And so we'll talk about plastic or ductile stuff and then brittle stuff in our last week and a half of class. But basically, it's that idea of like, if you squeeze something, it's gonna squish. So like if you, I don't know if you've ever seen, do any of you follow that gripping food with force Twitter? If you don't, it's definitely pretty cursed, but pretty funny. It's where people will take food and just, I mean, it's exactly what it says. They'll grip it. And usually what happens is they'll show the solid piece of food and then they'll show it like squishing out of their hand. And it's kind of terrible. But what do you, I mean, but you see it squish out, right? Like it doesn't generally, except for that guy that was like trying to squish a potato. Like if it's cooked food, it's going to squeeze out the sides, right? Like it goes splat, you splatter things. Or like when you splat a bug against your windshield, it just goes everywhere. So this is that same idea as when you squeeze a rock with force, it's going to go out either side. And so in this case, the grains of the rock become elliptical, perpendicular to the direction that you're squeezing. So in this case on the right, if you're squeezing the rock from horizontally, it's going to elongate vertically. And if you were squeezing it vertically, it would elongate horizontally. Does that make sense? So you can definitely tell the direction of the squishing by the direction of the deformation, by the amount, the way these things are elongated. And so while this is mostly about pressure, it has to be warm enough that things can squish, but it also can't be too warm that things melt. So mostly pressure, but heat is involved. Any questions about that? I wonder if I should tell the person who runs that Twitter that I used it in a geology class. I'm sure they wouldn't notice. They have like zillions of followers. Anyway, any questions about this? Cool. So I told you they're going to be charts. And so this chart is the last thing we're going to talk about today. We're going to get back to this next time. So we're going to end a little early today, but not before this chart. So we've been talking a lot about all of these processes that happen. We talk about how much temperature, how much pressure. And there's a bunch of crazy freaking minerals that form in metamorphic rocks. Like a lot of the rarest, weirdest minerals on Earth form in metamorphic conditions, just because of the way things break apart and come back together. You can get some super weird stuff in metamorphic rocks. But just in general, because the mineral situation is so variable, and because the protolith can be kind of anything, the way we first start to classify metamorphic intensity is called, in a way called metamorphic grade. And so metamorphic grade is literally just a description of how much change has occurred. It doesn't say what is in it. It doesn't say whether it's foliated or not. It doesn't really say anything about much, so much as just a categorization of temperature and pressure. How much temperature, how much pressure? If you're under high temperature or high pressure, it's probably high grade. If you're under both, it's certainly high grade. It's basically just a degree of intensity. And within each of these metamorphic grades, so there's a couple of different places they can happen, and you get different rocks in them. But this is just the broadest way of classification. So if you like our other chart, our igneous chart, this is a chart of temperature versus pressure or depth. But in this case, we're actually in a kind of different realm from igneous rocks because nothing is melting yet. This is actually colder than igneous rocks. So you're not going to get at a melting point. You're not going to have a liquidus or solidus on here because by definition, it has to be solid change for it to be a metamorphic rock. So under certain things, like if it's less than 10, like less than 15 kilometers deep, less than 5 kilobar, less than 250 degrees Celsius, this is not going to be metamorphic rocks. If you have igneous rocks that exist and are cooled already, they're just going to hang out and still be igneous rocks. This is the kind of situation where, if you remember, you do need some pressure to form sedimentary rocks. You need both cementation and compaction to lithify sediment. And that happens in this low pressure, low temperature realm that's labeled as non-metamorphic on this chart. But once you get past there, you can kind of follow 3 paths. It's kind of a choose your own adventure depending on what environment you're in. So in subduction zones, actually we'll talk about subduction zone last because it's a little different. So for contact metamorphism basically means a rock is coming in touch with something very hot and is baking. And the heat is enough to change the chemical structure without melting it. And so this usually happens like where you have igneous rocks near something else and they're really, really hot and they heat stuff up but don't melt it. And so all of those exist at pretty low temperature, pretty low pressure at only 2 kilobars, at only 10 kilometers deep. Like this is all very low depth, low pressure. And so you kind of low grade means it's, between 300 and 400 degrees Celsius, changes a little bit. Intermediate grade, you're cooking it a little more. Like it's, the burner is on medium. You get a certain degree of change, and then you crank that thing up to like, let's torch my food, turn the metamorphic stove up to high, you get high grade metamorphism up to actually here's your liquidus and your wet granite melt temperature and your wet basalt melt temperature. So contact metamorphism is low pressure and high heat that just comes from being near igneous rocks that are hot. Then the kind of metamorphism that's often a lot more intense and that we're actually going to spend more time talking about is in a mountain belt. So if you remember when I said at the beginning of class that most of the really intense metamorphism happens at convergent plate boundaries, and especially at continental collisions, because you're slamming a huge thick continent into another huge thick continent and you're making giant mountains. And so there's a lot of pressure. There's a huge, again, this is the equivalent of crashing 2 trucks into each other at full speed on the freeway. There's a lot of pressure and there's a lot of change. And if you also remember, just because continental plates are very thick, and when you crush them together, they squish out, again, like the squeezing continents with force, they squish out both below and above. You have this rock extending quite deep, this crustal rock extending quite deep into the earth. And so you can get high pressures and high depths. And then also because of that high depth, you get high temperature. So in mountain belt metamorphism, again, you still separate that between low grade, intermediate grade, and high grade. But, and the temperature ranges are similar, but the depth ranges are different. And so in this case, low grade is a kind of a wider range than intermediate grade, but generally this temperature range is similar. It's just the pressure is higher, which allows things to keep going without melting at higher temperatures. So do both of those make sense? So the last kind of metamorphism, you might notice subduction over here. So subduction is another convergent plate boundary, but in this case, you're shoving a plate under another plate. And that's still a very metamorphic environment, but it's different and because it's never very hot. Because it's always a cold oceanic plate subducting under something else, whether another oceanic plate or a continental plate, the temperature never gets very high. If you remember, the volcanoes and subduction zones all come from water being involved, not just from the heat of the plate itself. So in this case, though, it's shoving down pretty deep, and it's a very high pressure situation from crashing plates into each other. But because the temperature is very low, and also because there's always water involved, you get a very specific group of things. And so in a subduction zone, you always get what's called blue schist. And sometimes it is really blue, by the way, and it can actually be pretty blue. Sometimes it's kind of gray, it depends, but it can be pretty blue. And that's a very specific group of things that happen in subduction zones that are always low temperature and high pressure. And so this just describes the intensity, this categorization. So if I say something is high grade, you're gonna know that it's a high temperature. If I say something is low grade, you're gonna know that it's a low temperature. If you see something that's blue schist, you know that it formed in a subduction zone. So you know that it had low temperature and high pressure. Any questions about that? We will start with this again next time. But just looking ahead real quick. So this is the simplest thing. You can also sort of tell which metamorphic grade something is by what minerals are in it. Even though you can get super wacky minerals in metamorphic rocks, there's still very common ones that can tell you what you're dealing with. And so we'll talk about how to use this next time. But generally, like if you find clay, you know it's not high grade. If you find pyroxene, you know it's not low grade. And then also, based on those temperature and pressure and mineral conditions, there's categories of metamorphic rocks. So this chart combines both temperature, pressure, and mineral composition. And so we're going to start with this stuff next time, but just sort of these charts are in your book. I would strongly recommend taking a look at them before next class, just because I think it'll make it easier to really get a hang of what's going on. So with that, I'm done. Does anyone have any questions? And I will see you all on Wednesday. And if you do think of questions, again, you can just email me at any time. And you can come to office hours tomorrow. If you can't come to office hours tomorrow, but still want to talk on Zoom, just send me an email. We'll make an appointment.
Thank you.
Thank you. Have a good one, everyone. The rest of you taking notes, or are you just hanging out? All right, well, if you don't have any questions, I'm gonna end the lecture, but if you think of stuff later, just send me an email. Have a good rest of the day.